Hello, I'm Akifumi Ochiai. First of all, I would like to thank the organizers for giving me the chance to talk in this video. The title of my lecture video is Lagrangian mean curvature flows with generalized perpendicular symmetries. I'm going to talk about a way to construct invariant Lagrangian mean curvature flows with the use of special symmetries. Okay, there are two main goals in our talks. One is in general case, that is, to construct mean curvature flows by symmetries of Lie groups in Riemannian manifolds. Another one is a special case, that is, to construct Lagrangian mean curvature flows by generalized perpendicular symmetries of Lie groups in Calabi-Yau manifolds. There are some previous researches. In 2016, Yamamoto constructed generalized Lagrangian mean curvature flows in toric almost Calabi-Yau manifolds using moment maps and toric symmetries. In 2018, Konno constructed Lagrangian mean curvature flows in Calabi-Yau manifolds using moment maps and perpendicular symmetries of abelian actions. On the other hand, our researches are as follows. First, as general cases, we construct mean curvature flow in Riemannian manifolds using symmetries of general Lie group actions. Second, as special cases, we construct Lagrangian mean curvature flows in Calabi-Yau manifolds using moment maps and generalized perpendicular symmetries of general Lie group actions. In both cases, we do not necessarily assume that Lie group action is abelian. Okay. Now we show the overview of our method. Let M be an ambient Riemannian manifold, H a Lie group which acts on M, sigma an H invariant submanifold of M. Please look at this figure. Suppose that the submanifold sigma is this black surface. Okay, since sigma is H invariant, so the Lie group H also acts on sigma. For example, like this. We would like to construct the mean curvature flow of this invariant submanifold sigma. For this purpose, in step 1, we first find a nice submanifold V0, like this blue line. Next, in step 2, we consider the mean curvature flow of sigma. But in the first, we study only how V0 is deformed by the mean curvature flow of sigma. In this talk, we call this small deformation of V0 the restricted mean curvature flow. Okay, after studying the restricted mean curvature flow of V0, finally, in step 3, we have the mean curvature flow of whole sigma. By expanding the small deformation of V0 into the large deformation of sigma with the use of Lie group action. Okay, this is the overview of our method. Here, we review some fundamental facts on mean curvature flows. First, we define the deformation of an immersion. Let phi a manifold sigma, let phi from a manifold sigma to a manifold M be an immersion for a smooth map F from sigma cross a time interval 0t to M, which maps a point Pt to a point ftp, such that x0 equals phi. If ft is an immersion for any time t, then we call f the deformation of the immersion. Okay, this is our definition of deformations of immersions. Next, we define a special deformation of an immersion, that is, a mean curvature flow. Let phi from a manifold sigma to a Riemannian manifold Mg be an immersion. Then, the mean curvature flow f of phi is the deformation of phi, such that it is a smooth solution of the following partial differential equation. This equation means that the velocity vectors of the deformation large F of the left-hand side equal the mean curvature vector field of the deformed immersion capital Ft of the right-hand side at any t in 0t. Okay. It is known that a mean curvature flow preserves the Lagrangian condition in Kähler-Einstein manifolds. That is, if an ambient space is a Kähler-Einstein, and there exists a mean curvature flow of an initial Lagrangian immersion, then any deformed submanifold of the flow is also Lagrangian for each time. Now, we show a way to construct mean curvature flows in Riemannian manifolds with the use of symmetries of Lie group actions. That symmetry is called the property star in this talk. We assume the following setting star 2 as star 1. Let Mg be a Riemannian manifold, H a Lie group such that H acts on M, K a closed subgroup of H, V a submanifold of M such that V is in Mk, where this notation M super K is explained in the following definition 3. We use the following notations through this talk. Let V has star the center of the Lie coalgebra has star. Lk is a set of points P in L such that Hp equals K, where Hp is the isotropy subgroup at a point P, and L is any submanifold of M. And phi V is a map from H over K cross V to M, which maps a point HKP to a point HP. Okay. For the sake of the condition that V is in Mk, this map phi V is well defined. The rough image of the map phi V is the expansion of the submanifold V by the H action. Okay. Next, we define some symmetries of Lie group actions, which is called the property star in this talk. Under the setting star 1, if the map phi V is an immersion, and its mean curvature vectors are H invariant, i.e., it holds that the following equation star. Then we say that the submanifold V has the property star with respect to the H actions. Okay, this property indicates that the information of the mean curvature vector field of the immersion phi V is concentrated on the submanifold V, like this. Okay, next we define some notations in the following definition 5 and 6. Let V0 is a submanifold of M, such that V0 is in Mk, and it has the property star. Under the setting star 1, if there exists a deformation small f of V0 in Mk, and Vt, which is FTV, also has a property star, then we say that the deformation small f preserves the property star of V0. Okay. Next, we define the expansion of a deformation by Lie group actions. That is, we obtain a large deformation capital F from a small deformation small f by the H action as follows. Under the setting star 1, suppose that there exists a deformation small f. If the map phi Vt is an immersion for any time t, then we can define the deformation capital F of phi V0. And this is the capital F by the following map capital F. This map capital F expands the small deformation small f into the large deformation capital F by the H action. Okay. Now we define the expansion. Now we show a way to construct invariant mean curvature flows in Riemannian manifolds by using the property star. Let Mg be an ambient Riemannian manifold, H a Lie group which acts on M, K a closed subgroup of H. Now let sigma be an H invariant submanifold of M like this blue surface. Since sigma is H invariant, the Lie group H also acts on sigma, for example, like this. Okay, we would like to construct the mean curvature flow of sigma. For this purpose, we first take a nice submanifold V0 with the property star, like this, with the property star, such that V0 is in Mk and HV0 equals sigma. Okay. Then we suppose the followings. Theorem 7. Under the setting star 2, suppose that there exists a deformation small f of V0, like this. A deformation small f of V0 with its expansion capital F, like this. This is a large deformation, capital F. Okay, satisfying the following condition 1 and 2. The condition 1, for any time t and any point p in V0, the following equation holds. This is the restricted mean curvature flow condition of V0. This condition means that the small deformation small f is moved by the mean curvature flow of sigma. Okay, next, the condition 2. F preserves the property star. This condition means that the information of the evolution of mean curvature vector fields of whole sigma is concentrated on the small deformation, small f. Concentrated on this small part. Okay, then the maps Ft is the mean curvature flow of V0. Okay, this is the theorem 7. This theorem is our basic tool to construct invariant mean curvature flow. Okay, this part ends here. In the next part, we start with some basic examples of theorem 7.